So before we move on to differentiability and continuity and how they kind of play together, we're going to do one more definition or one more example using the limit definition of derivatives. So the function we are going to use is 16 minus x squared. I am really bad at those x's. X squared over 4. Now that looks something like, let's see, something like this. So if we're going to use our limit definition on this problem, if you recall, it's going to be, we'll just write it out one more time, practice makes perfect, limit as h goes to 0 of f of x plus h minus f of x over h. And remember, this is just a fancy way of saying dy over dx. And the limit just makes it, instead of an estimate, it makes it the actual value. So now let's try and evaluate this. So if we plug in f of x plus h, we're going to have 16 minus x plus h over x plus h squared over 4 minus 16. So that's f of x plus h. Here is f of x, 16 minus x squared over 4, and that's all over h. So, once again, x plus h squared is x squared plus 2xh plus h squared. So, 16 minus x squared, and we gotta just either distribute it or keep a parentheses, x squared plus 2xh plus h squared all over 4 minus 16 minus x squared over 4, and that is also in parentheses, all over h. Sorry, that is a bad h. And that one got a lot better. So moving on, let's do some simplifying. X squared plus 2xh plus h squared over 4. Well, if you can see here, we've got 16 minus 16, that's going to cancel out. And here we've got negative x squared over 4, so if we were to distribute or break these all up, here I'll just draw it like this. Another way to draw this would be as each part divided by 4. So that's divided by 4, that's divided by 4, that's divided by 4. And that negative x squared over 4 has a plus x squared over 4 because we have a minus times a minus. See, there's two of them there. So that is going to cancel out with that. We're going to have 2xh over 4 plus h squared over 4. Once again, we can factor out an h, and I'll just leave that over 4 in the denominator. So if we factor out an h squared, we're going to have, let's see, 2x plus h. So 2x plus h. We factored out an h. There was still an over 4. And that is all over h. And if you remember dividing, this might look like there's too many divisions, but remember that dividing by h, or dividing by anything, is the same as multiplying by the reciprocal. So if we take this and divide by h, it's equivalent to just saying that it's multiplying by 1 over h. So times 1 over h, which then means we can bring that h inside the parentheses. So I'm going to rewrite that. So 4h. Now that h cancels with that, and we've got 2x plus h over 4. Now, remember, limit. All this simplifying I've been doing, I should have been writing limit as h goes to 0 in front of all of it, but that is so space and time intensive that I didn't want to do it. So I'm just going to do my simplification and redraw that. Remember that that's what I was doing at the end. So the limit as h goes to, sorry, that should not be infinity. Didn't mean to confuse you. It should be 0. Limit as h goes to 0, well, once again, we can just straight plug that 0 in, and we get 2x over 4, which is 1/2 x. So, what is... did I make an algebra mistake? There should be a minus in there somewhere. Oh, right, I forgot. From the last one, we had to distribute that minus through. So it should be minus 2x plus h. I forgot to distribute it through, sorry. So minus 1/2 x is the limit as h goes to 0. And we were plugging it in at, we can pick any point, but let's plug in, I don't know, 2 again. That seems to be common. So the slope of that function, that 16 minus x squared at 2, which would be right around here, I suppose. Since it was minus 1/2 and we're plugging in 2, it's just going to be minus 1. So the dy dx at 2 is equal to negative 1. So that line, which I guess that doesn't really have a slope of 1, more like this. Oh, come on. There we go. More like that, and then if they were touching right there, is the slope. So there's one more example of using the limit definition in a slightly more complex problem, but really all the algebra tends to work out nicely, at least on quadratic problems. Once you get into higher powers, you've got to expand things more, and when you're doing, trig, you're going to have to use some trig identities, so I'm trying to keep it simple and explain, more of the theory as opposed to the algebra. But now let's go into how derivatives interplay with continuity. So if you remember way back when I mentioned, a couple videos ago, I mentioned a cusp, and that was when a function did something like this. Sorry, I'll keep it in black. Did something like this. There was some, boom, like something that came together like that wasn't, I don't know, you could tell it was kind of like it got pinched somewhere. And the function is continuous because if you remember, two ways to think about it are I didn't pick up my stylus when I drew that, but also the limit from the left is the same as the limit from the right. They're equal, therefore the function is continuous. However, remember the derivative is the slope. I can calculate a slope here because that makes sense to have a slope there. There's some tangent line that could fit to it. I can calculate the slope here. I can calculate the slope. That was close. I can calculate the slope there. But here, how do you calculate a tangent line there? That just doesn't make sense. It's a cusp. There's no fluid transition. You went from a slope of, let me get rid of those. You went from a slope of this at one side immediately to a slope of this. There's no transition. You have like an infinite number of slopes at that one point. So that point, although continuous, is not differentiable. Another way of saying it is that differentiability implies continuity. If something is differentiable, if I can take the derivative, like here, then it must be continuous. If I can take the derivative, it has to be continuous. But the reverse is not true. Just because it's continuous does not mean it's differentiable. Alright, so that was another example of using the limit definition of derivatives, which, once again, just so you hear it again, excuse me, it's the limit as h goes to 0 of f of x plus h minus f of x all over h, the limit as h goes to 0. H. And remember, that's just dy over dx. We're just making it complicated and making it a little bit more rigorous. Next time we'll go over sketches of the derivatives, kind of a more intuitive way to look at derivatives. And then we'll also get into the shorthand ways of writing derivatives. Remember, I gave you that hint, I think, one video ago, and I'll tell you what the formal way of finding those derivatives a lot more easily than doing the limit definition proof is. So, ta-ta for now.